Okay. Great. Just a second. So also Michael, like the other two speakers, has been in every edition of the ViperCon as well. So thanks for donating your time in that sense. Okay. Maybe your microphone. It's visible. I'm not sure you're audible, Michael, at the moment.
Can you see me?
Yes, now I can see you and hear you as well. Perfect. And your slides are also very nice.
Yeah. Okay.
Thank you so much.
So, well, my talk will be more of a research talk. Okay. There are challenges still in the perovskite solar field. And the predecessors, of course, are very impressive talks. So it's another challenge to just talk after them. Okay. So yeah, some of the highlights which we are researching at the moment, we are interested in large bandgap tandem cells. And that's because the solar fuel production is something that we are really passionate about. And it's certainly kicking in a lot of investment in this field. Perovskite investments, I mean, commercial companies now moving in. So the researchers there certainly addressing the solar fuel issue is an important one. And so we have collaborated with Professor Tan from Nanjing University and just on the wide bandgap perovskites, which is an issue. I mean, in tandems you need a high voltage wide bandgap material, which has about a bandgap around 1.7, 1.8. And so there's some progress there which I want to report on. It's still unpublished. And okay. Yeah, so our motivation, as I mentioned to you, we have, of course, we want to contribute to the growth in photovoltaics. And Namgyu showed that science paper, it's really a challenge to go to 75 terawatt. It means something like a 100-fold increase in the installation speed would have to, in the next 25 years. So installation rate would have to go up by a factor of 10 to meet that target, okay? As presently, we have 300 gigawatt per year power installed worldwide. Has to go up to 3 terawatts, and that's really a challenge. And don't forget, I mean, when we say 75 terawatt, that's peak power, and so the average is 5 times less. So we're still not contributing to even half of the energy supply of the Earth by reaching 75 terawatts. Anyway, so consumption of power goes up, perovskite will contribute to the photovoltaic challenge. However, we also have to think about storage, and solar fuels is the way to go. Certainly hydrogen will emerge as a major energy carrier, but also the CO2 conversion is a very important point. So we are interested in these topics. And just to point out to you that if you want to make 1 megawatt peak power, you need 7 tons of silicon. And that's really a lot. And it has to be extremely pure. I mean, there are 9 nines in the purity number, 99 point, and there's 7 more nines. So, I mean, you can argue that this is a lot of expensive material, expensive from the energy point of view. And the price has come down because of mass production. However, we still have a very big carbon footprint for silicon. It's about 50 grams CO2 per kilowatt hour. And so, for example, we look at alternative technologies. Well, the perovskite looks better. But look at the Dyson size. We are still working on Dyson size. 10 kilograms, it looks 1,000 times less, almost. So here's a motivation to work on alternative photovoltaic systems. And so, yeah. Yeah, so I'm really glad that the question of how to template the perovskite crystal growth has been brought up by Namgyu, and also in the questions that were asked. Because I mean, just think about it. If you use solution processing, it would be naive to believe that the support has no effect on the crystal formation. Okay, so you have to prepare that support for directing crystal growth. I think that's a way to get, for example, faceted. I have one item I'll bring up later, the uniaxial 100 surface facets. That is possible just by using additives, something very, very interesting going on. And so I'll be mainly talking about this because I think it's an interesting and research topic. And at the end, we show that actually we can, by using this templating approach, we can make a large band gap, 1.7 volts, that have about 1.37 volts open circuit voltage. And with that, we can reach those numbers here with the tandems. And I feel that the postcard tandems, probably I'm getting a lot of enemies now, but they're more promising than silicon postcard. And I think Martin Green has the same opinion because these materials are very different. When gap changes temperature in opposite sense, and organic materials, expansion coefficient. I think there's a really good reasons to go in perovskite tandem. And so let's start now with that's a published article. You can read it, and so be fairly brief on this one. Oops. So yeah, put this down here. So the first study I will be dealing with is is a PIN structure, and so it's work that we carried out with the Fudan University and Professor Chang also. And so that's an amazing observation. In the beginning, I didn't believe it. If you take aminoindane hydrochloride, it makes a 2D perovskite with formamidinium and methyl ammonium cations. And yeah, if you add this FB in the starting solution, okay, of the perovskite, and then a very small amount, just 1 milligram per milliliter, and it does direct the growth of the perovskite. So how is that possible? Well, what happens is when you spread the perovskite, there's a 2D self-assembly of 2D at the interface with the nickel oxide, aluminum oxide. There's a kind of this a whole specific interface. So we have PDA, nickel oxide, some aluminum oxide. Here you see the Venn diagram. Okay, so on this interface you put down this. There's a self-assembly of 2D perovskite, and there's proof for that. Okay. Now, but the surprising observation is if you just make that perovskite per se, and then as a 2D layer, and it doesn't work as well because it produces an electronically blocking interface. Everybody has to ask the question: if I have a 2D perovskite that's coplanar with the support, well, how does the charge get through that spacer layer? And so, yeah, so for some fortunate reasons, the self-assembly still has the property to let the holes get through to the hole select contact. However, it is also directing the growth, and so you get better crystals. I'm not saying that you have the surface. Later, I will show you a case where we have facet-specific growth and uniaxial 100 surface form. However, this is not the case. It's just you get better performance, and show you in a minute. So there is a self-assembly going on, and I think that's something that is new, and people have kind of been skeptical. Why doesn't it self-assemble on the other interface? And and so the reason is it has strong interactions with the HDR layer. Okay, so that's what the other layer is against there, and so that's a different interface. And so, yeah, I hope I have made that clear. There's just some evidence. You can see we can see when we take the GVAX at a wider angle, we see the 2D layer formed. But if you take it at a narrow angle, where we mainly probe the surface of the perovskite, we don't see it. So it's buried. It's a buried junction. So the 2D layers actually formed at the bottom of the perovskite, and they contact with the HTL. And that's also, the luminescence shows that, because if you look at this luminescence, we take it from the bottom side, the luminescence, we can see it, the absorption, we can see it. However, from the top, you cannot. And yeah, nature just helps us, spontaneous formation of this. And so it's a 2-amino indane that does that for you. And here's it's a Rudolph-Popper structure. It's mainly n=3. All this has been sorted out. And if you take the cryogenic focus on beam analysis, you can see actually a 2D layer on the bottom. So there's evidence. It's not fantasy or speculation. There's several independent experiments show that this happens. So I hope I have convinced you. And so here we show that it depends how much you add to the starting solution. So 1.5 milligram per milliliter, that's very little, but that gives you the best performance. And yeah, and the PCEs for that's a PIN structure. That's a high PCA, at least it was at the time when this paper was published. And so, yeah, and also what looks very nice is the ideality factor close to 1. I mean, that tells you can get a very good fill factor, and you get fill factor over 80%. Let's just go back, yeah. So, and then it comes the photovoltaic performance, so you can get over 25%, and which is a MA-free system, okay? So just formamidinium cesium. And you always want to point out, the number 1 in some areas. So that's a record for MA-free at that time, okay? But more importantly, what should I say? The stability is excellent. I mean, MPP tracking shows hardly any degradation over 1,500 hours full light, and also the DMP test is very good. I mean, it's less than 10% degradation over 1,200 hours. So, what is the amazing facet of this? If we draw the facet, is that a little bit of this compound is the starting solution. There's all these magic things for you. Yeah. So I recommend you to buy some amino indane hydrogen fluoride. Okay. So now in the same way, and we have been struggling to get a paper published that also reports on directed growth specters, this time on an NIP structure. And so the NIP structure is such that when you put the perovskite down, it will see the electron selective contact first. And these are nanocrystals of quantum dots of tin oxide. That's our electron selective contact. However, this contact can be improved. And so here it is shown that by just treating the tin oxide quantum dots with guanidine and sulfate, you can get that growth. But I should mention to you, actually, the experiment was done with a two-step method. It's we first put down the lead iodide, and then it's converted. Okay. So what is really directed by this surface absorbed guanidinium sulfate is the formation of the lead iodide, which is really coplanar. And there are two reasons for that. I'll explain to you in a minute. But as a result, we get much better efficiency and also stability-wise. I mean, this is very similar to what I just showed you, but this time for an NIP structure. And so it's wrong to say NIP structures are less stable then PIN. If you have that opinion, I recommend you to read Anders Schagfeld's paper that just came out in Nature Energy. It shows 4,000 hours stability for NIP. Well, that's for MPP tracking, and 1%, that's the error limit degradation. Okay, so back to our work. So how does that happen? How does the, well, first of all, just the deposition was done in a sequential manner. I like to brag about this paper we published in Nature. There's also lots of citations. And also tell you, this was the first certified perovskite solar cell. And it was, you can see that the certification was giving us over 14%. And he had published something like 15, but we put that certificate in the Nature paper. Okay. And also one other thing that is important is in this paper, we showed that when we impregnated the Ti2 film with the perovskite, it filled the pore space and formed a capping layer. That gave us the higher currents, okay? And that moved the efficiency from 10 to 15%. That's a 50% improvement, okay, within a couple of years. And so, yeah, and so the reason why this direction happens is that twofold. The sulfate is gonadinium sulfate. The sulfate interacts with the tin oxide, the OH groups, and forms an HSO4 minus anion on surface that produces a dipole, and that dipole directs the growth. And the sulfate also interacts with lead and passivates lead, and so you get that better performance. Two actions that are. I hope that you will soon see that paper published. And so now we come to the final part. How am I doing, Mark? I still have a few minutes, okay.
So we're good, you have 12 minutes left. Okay,
good, yeah. So then now comes something very serious. So we want to make a uniaxial growth. And how was that possible? Well, there's also an additive engineering. And this time, please listen very carefully, we added the phenylethylammonium, which is a very well-known 2D forming agent, to this anti-solvent, not to the but to the anti-solvent. This is different from the amino indane, which was added to the initial starting solution, okay? So when you do that, you get stunning changes. And so the growth of the crystallization of the perovskite is directed by a 2D film that also forms on the substrate spontaneously, okay? And so this is something that is under review in Nature Materials. And so we hope that it will go through, and later we will use that material as a wide bandgap perovskite, okay? So it's a wide bandgap material, and the amazing result we got by this simple treatment, okay, was that the VOC went up to 1.373. That's very hard to get this for 1.78. So we're getting 400 millivolt deficit, okay? Now, even I want to point out it's a little bit better than what Tom Miyazaki had shown, okay? We're all very proud about these small differences. And so we're moving towards higher voltages for these wider bandgap materials. And so actually this is a very important issue for the perovskite tandems, because the wide bandgap material is a top cell in this. And if your voltage is bad, the top cell, you cannot compete with other tandem systems. And so, and so how come this all happens? First of all, I should mention to you, the best result was obtained when the phenylethyl was added together with ammonium. So That we call this MSPA. SPA means it was added as an antisolvent to the antisolvent, and DA was directly added. And so you see if you look at the right side, I mean, the critical thing is seen here. That's a ratio of 100 to 110 peaks, okay, in the XRD. You can see this goes from 1 to 50. That's really stunning. Okay? By just adding this in the antisolvent, okay. And so yeah, so what you do is you get a real nice cubic, and that is also confirmed by the GVAX. So if you look in the GVAX, you see control, and this is a 101. This is the 101 circle, okay. And so we see that nothing happens much with the DA. Okay, there's some reflections here, but then with the SPA, that means we have not used methyl ammonium, we have used formamidinium. So you get some nice black reflections. But then if you use the methyl ammonium, you get just one peak, believe it or not, and it's at the lattice vector 0. That means you have vertical orientation. Here you have an orientation, some vertical, and that's 45 angles, okay? So you have the cube is on the tip, sitting on the tip, and same thing here on the left. So you can interpret easily these GVAX patterns. Yeah, as clear as you can get it, okay? And I wanted to point out to you again that this is now, we're going back to PIN structure, where the P-type, this whole selective support is a nickel oxide SAM. That's now becoming very, very fashionable, but we will see soon the nickel oxide will disappear, okay? Because SAM's getting better and better. And so, yeah, SAM means self-assembled monolayer. It's not really a self-assembled monolayer. This is kind of like a spaghetti structure of the surfactant used. And so, yeah, so this is the stunning thing. So here we have uniaxial 100 crystals that form the film. Very impressive. And so that leads to some desirable optical properties, the voltage deficit goes down, and that's of course what we need for the wide band gap. And you can see the fill factor, also the losses there. You minimize these losses, especially transport. And yeah, the emission is so that's lifetime of the luminescence, time of luminescence. All this looks very good. And also, I mean, one critical thing is electroluminescence, external quantum efficiency. So you have to look at the point here on the x-axis, which is the short circuit current. Now that may be around here. So we're getting over 1%. Of course, one can get much better results with NIP, but I'm just telling you that for a PIN structure of this band gap, it looks good. And so, yeah, and here's the photovoltaic performance. PC 21%, okay? Well, that's, here we talk. That's the top layer. If we look into the silicon tandem, as both guys say, they are usually around 20%, I think. Well, I will speculate, okay. And so that's the current, and this is the SPO. Yeah, here are the critical data for that top cell. Yeah, and finally, I have 3 minutes left to do the final score. So a tandem cell was built, and I mean, using this MSPA, you can see how the performance goes. It's reflected in the tandem cell. Okay? So you're getting some 2.1 VOC. I mean, the best was over 2.2 volts, and yeah. So I mean, almost all the parameters go up, and yeah, including the power conversion efficiency, and yeah, stability-wise, well, you still have some work to do, but that's true for all tandems, okay? And because, I mean, it's not so bad. You get 10% over beginnings, I think, but there is some kind of a hump here. So that's a bottom cell, I think. There's an issue with the bottom cell because we had excellent stability for the top cell. And the bottom cell has tin in it, and so still you have to work on those mixed tin formulations. So with that, I just want to tell you that we are applying these high voltage cells for making hydrogen from water, but that's a separate talk, and it would be another half an hour, so I'd rather stop here. And yeah, I just want to show you our group, and what you see behind is the Congress Center wall, is CSC panels, and yeah, these are our co-workers, and we are an international team. We have people from China, Korea, Spain, USA, India, but we are a very closely knit group, and move forward. Thank you.
Thank you, Michael, also on behalf of the audience for this fantastic talk and the very impressive results. Let's hope they all come out soon with the gods of the journals, you know. So, of course, there are many questions again, and maybe I can ask you two. One by Amir Habibi, who's saying, thank you, Professor Pretzel. What are the primary challenges currently faced in the development of perovskite tandem solar cells? And what innovative strategies can be implemented to overcome these hurdles? So that's a very broad question.
Yeah, it's a good question. And I think we should all work on those because the payoff will be huge. I mean, I don't want to do any bad mouthing about the silicon perovskite tandem, but I mentioned to you what Martin Green's opinion is, okay? So anyway, to answer your question, the main challenge was, one of the main challenges is, of course, that top cell. You still have a 400 millivolt deficit, which we have to compare the 310 for gallium arsenide. And our best NIP cells, they are like gallium arsenide. They have maybe around 310, 315 voltage deficit. And so you still have to work on this. And I think the critical interface is the one that with the perovskite, with the C60, it's really lousy interface, okay? You have to do something about that interface. And the weakness of this particular cell is it still uses the C60. And C60 is not acceptable. It would have to be evaporated, and God knows whether evaporation will ever work for perovskite production. It was very slow. And so, yeah, so there's one challenge. And the other challenge you saw is the bottom cell. I mean, the tin lead, they're widely investigated, but we still have to do more about stability, okay, to control the oxidation of tin 2 to tin 4. And there's progress now, but there has to more research on that.
Yeah, thank you. That's very interesting. Then also we have another question again by Max Grzesiak asking, thank you for presenting such interesting results on wide bandgap perovskite solar cells. Can you also comment on their operational stability of the wide bandgaps as single junctions?
Yeah, I thought I had showed you that. Let's see. Oh, yeah, I didn't. Yeah, yes, they are excellent. I mean, the stability of these PIN structures. I thought I had put a slide in, but I must have missed that.
Probably the demixing could be a concern, for example.
Yeah, well, yes, the demixing, you're right. This is something one has still to worry about. There are ways to mitigate it, and again, additive engineering helps. But yes, a good point. The demixing, that's a general for all materials that have a wide band gap. Yeah, you're right. That's an issue, okay. But Well, I really, I don't have the data to show. I thought that this looked actually pretty good, given the fact. But we have to be very careful with these. The mixing, people report, well, I solved the problem, but you have to be really illuminate at high intensity on long time to get to see that effect. Okay.
So somebody else is asking exactly that question now, Nur Sultan Musa Kanuli. Yeah, I mean, I think I totally agree. The wide band gaps are now the big frontier, and the demixing is idiosyncratic to them.
Yeah, yeah. I should have mentioned that as a problem to be still tackled. We have worked on that, and we have published data that look promising with the additive engineering, and other people have. But I think we need to be modest there and say we need more work and show that. And can we find perhaps other materials that have the right band gap? And I think there's probably is another way, just the cesium-rich formulation. I mean, that's a good point.
Mm-hmm. Thank you so much, Michael. I mean, there are more questions as always in these situations. I want to thank you on behalf of the audience once more for your fantastic talk and also for sharing so generously